Howdy, I'm Dr. Rob Parks, Deputy Director of the George Mason Observatory. This video is a recording of a talk that Dr. Josh Pepper gave entitled The Search for Extraterrestrial Life. There was a hitch during the recording process. For some reason, the camera decided to turn itself off right after my introduction and right before the beginning of his talk. Now, Dr. Pepper is currently working with NASA, and so the important bit that was missing is the disclaimer that his views and conclusions within this talk do not represent the views and conclusions of NASA as a whole. Now, his talk primarily is devoted to the discovery and characterization of exoplanets, and then at the end, he ties that into what sorts of implication that leads to in terms of trying to find life beyond our solar system. Well, with that said and done, I will leave you to it. Like I said, his portion of the video, the first 5 or 6 minutes are cut, but I'm sure you can quickly get up to speed as to what he was talking about. So, I hope you enjoy, and please come back for more videos on this channel about what we do here at the observatory.
Hello folks, and welcome to George Mason Observatory. I am Dr. Rob Parks. I am the Deputy Director here at our observatory. And again, welcome to our Evening Under the Stars program. Before I get into that, what I'd like to do is I'd like to give you sort of a brief overview of what our observatory is and the things that we have done with it. One of the silver linings of the pandemic is that it accelerated something we wanted to do anyway. Most research-based telescopes, you don't actually go to the telescope anymore, sadly, because I will probably never get to go to Hawaii. But, because most of the telescopes now have the option to observe remotely. You can observe, Peter, our director, he observes from using a telescope in Hawaii here quite often. So, before the pandemic, we would have to go up to the control room, which you will all see. We'd have to sit at that desk and we'd have to control the telescope from there. However, now, if you have the proper credentials, you can log in anywhere, and I've been told, I don't know why, but I've told this, but I've been told that some of our students will lounge around in their pajamas and take observations. Didn't really need to know the pajamas bit, but it was good to know that they were, comfy at home. So you can observe really anywhere around the world using our telescope if you have a stable internet connection. The images that you see around it, those are taken by the students. Our telescope, probably by, just off the top of my head, I would say that from a percentage of use, it is almost as used as much for student observing than it is for research observing. Primarily this type of work, which is just basically students who are having fun or are learning how to do this type of observation in one of our observation classes. Now, those are, as I said, they were student taken, they are student processed. They will go into up there more about that processing, but these are early versions. These are some of our more talented astrophotographers. The one on the left is the Cocoon Nebula. That is 18 hours worth of data. So what happened was that they took observations over multiple nights and then were able to combine that to get what we lovingly refer to as the GMU deep sky image. And then we're also doing the same thing for this galaxy, which has the lovely romantic name of IC something or other, 257. So that is probably around 10 to 12 hours, I think. Still working for that. So tonight, I need to change that. The next speaker, who I just got confirmation today, actually, is Dr. James Haber. He is going to be talking about expeditions to Mars, the rovers that have been sent to Mars. Next talk is on the 27th, I think. Yeah, 27th. And the talks will generally be 30 to 45 minutes long, typically with a brief Q&A, although I believe Dr. Pepper is probably going to section off parts of his talk and then allow people to ask questions related to those sections. if you'd like. And of course, you can hold your questions till the end. And then afterward, we will take you up usually with our guides. We have Aiden, we have Yasir, we have Jonathan over here. They will allow you access up to the observatory, and I think it's clear enough that we are seeing Jupiter, or not Jupiter, the moon, and we might see Jupiter later on. This is not a one-person operation. Dr. Peter Plavchad, who cannot be here tonight, is the director. As I've said, I'm the deputy director. Kevin Collins and M. Thanya Pong. M was around here somewhere. You'll probably see him upstairs. They are our observatory teaching assistants. They are vital in the operation of our telescope and these programs. Jonathan has another hat, which he wears, which is the president of the Friends of the Observatory student organization, which is now currently, what, sixth largest? Yeah, sixth largest in the on campus. When you took it over, we were not sixth by any stretch of the imagination. We have grown huge. We have a number of tour guides who also assist us. If you're interested in what we're doing here, please contact us via X, email. We also have a Facebook. We also have a YouTube channel, so forth and on. Friends of the Observatory, I would not feel right if I didn't plug them. If you are a student here at the Observatory or considering being a student here, say in, what, 10 years? Please join the Friends of the Observatory. That is a, what do you call this, QR code that you can use to get onto the Discord. Jonathan is, of course, the president. We have Sydney, Joe S., and Benjamin, and Chris, how do you spell it? Jesse, are meetings. They have meetings monthly, and they get to use the 32-inch telescope pretty much unsupervised. We just hang out over on Discord and make sure that the telescope isn't on fire. But outside of that, they have carte blanche as to what they want to look at and for how long they want to look at. And to help with potential star parties, we are selling stickers. So if you're interested in getting some very high quality stickers of images that we have taken here by them, please come see Jonathan.
I'm not holding back to the I'm just helping you with
If you're interested in what we do here as an organization, I highly recommend subscribing to our newsletter, The Moon, the Mason Observatory Outreach Newsletter. In it, we have facts about what we're doing. We highlight certain students. We highlight just stories of the day, such as Intuitive Machines, a private corporation, may in fact be the first corporation to land successfully on the moon, and they will be beating Russia at doing so. Suck at Russia. We also have other astronomy education along with that. When I got here in 2020, at the height of the pandemic, one of the things that I greatly wanted to do was to increase our outreach program. We have an inflatable planetarium, which we have taken out to Cub Scout events. If you are interested in that sort of thing, please let me know, and we can schedule that. This sort of thing, unfortunately, does require money. So if you would like to help facilitate our outreach program by becoming a financial backer, please consider becoming a patron of the observatory. And as you can see in the bottom right, that is my name. I put my money where my mouth is. So, that all being said, I'd like to introduce Dr. Josh Pepper. I believe I first met you when you gave a talk at GSU, Georgia State University.
That's right.
Yes, about KELT, which in lovely astronomer fashion stands for the kilodegree extremely little telescope. So we tend to get it on the nose. I'm sure he could talk more about it. He has discovered, what, 26 hot Jupiter?
Yep. 26 planets.
26 planets? Okay.
Yep.
He is teaching he's a professor at Lehigh University, but is now with NASA for a year? Or
A couple of years now.
A couple of years now? So he kindly agreed to give us a talk, and he's going to be talking about the search for extraterrestrial life. Because he is someone who finds exoplanets and characterizes them, he is going to put it in that context. And he has a tool that he just showed me today, Eyes on Exoplanets, which is fantastic. highly recommend you look at it after he's done.
I'll show a demonstration of it in the middle of the talk.
So, without further ado,
All right. So what really distinguishes them is what they're made out of. Terrestrial planets like the Earth, even though we have all of this beautiful air and water and forests and life, really we're a big hunk of rock and metal. You start digging down more than a few dozen feet into the Earth and you're just going to be hitting rock, and then it's just continuously rock and metal all the way down to the center of the Earth. We're a big ball of rock and metal. Then we've got the ice giants like Neptune and Uranus, which are mostly, not entirely, but mostly made out of what we would call the ices. And these are things like water and water ice, but also methane and carbon dioxide and ammonia and things that would melt if it wasn't really, really cold. And then you've got the gas giants, Jupiter and Saturn, which are made almost entirely out of gas. That's why we call them the gas giants. And the specific gas that they're made out of is hydrogen and helium. But these three types of planets, I've lined them up here so they all look pretty, but the other key thing to remember whenever you're thinking about astronomy and space is that space is big, and things in space are vastly different in size compared to each other, even though we like to use images like this that show them kind of in similar sizes. In reality, these different planet types, this is how big they are compared to each other. Gas giants like Jupiter are way bigger than the terrestrial planets like Earth and Mars and Venus and Mercury. And the ice giants are in between in terms of that. So this is what we have to think about when we start thinking about why do we find certain kinds of planets and not others, is partly because of this. Because it's generally easier to find really big and massive planets like gas giants than it is to find small rocky planets like Earth's. So we want to go find these planets, and these planets are orbiting other stars. You look out into the sky and you see all those beautiful points of light, and you could try to look really, really close and see if there's a planet there. Well, here's the challenge that we have. Planets are dim compared to their stars, and they live right next to the star. They're orbiting the star. So from our perspective, those planets are right next to the star. And the comparison we like to use is imagine staring at an enormous searchlight that's brighter than all of the car headlights or other street lights that you'll see, and it's pointing directly at you. Looking for a planet orbiting the star is like looking for a firefly crawling on the edge of a searchlight. In fact, it's actually a lot harder than that, but that's the comparison we like to use. So how do we do this? Well, the way that we try to do this is to try to do what we can using fancy equipment to block the light of the star so that we can catch the light of the planet. And if you block the light of the star, then you can see our little friendly firefly just crawling along the edge there. But this is really hard, as I said, because the stars are much brighter than the planets, and because the planets are really close to the star. So the comparison is that at 10 parsecs, which is about 30 light years away, that's about how far a nearby star in our own galaxy is, at that distance, a Earth-like planet orbiting that star is 0.1 arc seconds away. 0.1 arc seconds is an angle. It's a very, very tiny angle. It's the angle that would be the width of a human hair that was 2 football fields away from you. That's how close the planet and the star are, and the star is a lot brighter than the planet. How much brighter? Well, it depends on the kind of planet. This is an image. My astronomer friends have seen this many, many, many times, but it's a great image. This is a star called HR 8799. Yeah, 8799. And what we're seeing here is images of this star taken over the course of many years. If you look at the lower left, as you can see from 2011 or 2009 to like 2016. Over that time, what the astronomers did was they used a special piece of equipment called a coronagraph to block out the light of the central star so that you can see planets orbiting the star moving around like that. This was wildly successful. It's really exciting, but this is close to the state of the art of what we can do. And The tricky thing here is that you'll see this little bar down here that says 20 AU, and AU stands for an astronomical unit. It's how far the Earth is from the sun. And there's 20 of these in this scale bar. So that means that the innermost of these planets is about 15 or so AUs away from the star itself, meaning that all of these planets here are way farther away from their star than the Earth is from our sun. Another thing is that all of these 4 planets are huge, massive gas giant planets, as big as or even bigger than Jupiter. So the only reason that we see them is not because these planets are reflecting the light of their star at us, which is when we see our planets in our solar system, when we look at a telescope, the reason we see them is because we see the light reflected off of their surfaces from our sun. That's not what's going on here. These planets are very young. This whole solar system is only a few tens of millions of years old, which in astronomical terms is a very, very young solar system. So these planets are still glowing red hot from the heat of recently having formed, of coming together from a gas cloud that they originally formed from. And so the only reason that we can actually see these planets is because they are far from their star, they are very big and massive like Jupiter's, and they're glowing red hot from the heat of recently being formed. In this case, these planets are I think, either 10,000 or 100,000 times fainter than their star. And that's the limit that we can do. If we want to see an Earth-like planet, the size of the Earth at the same distance from its star as we are from our sun, and a small planet, we need to do 1,000,000 times better than that. And this is how far we've come over the course of many, many years. And we need to get a lot better. We're working on that. But we need to do roughly 1,000,000 times better than what we did here if we want to find an Earth around a star like our sun. But there's other ways of finding exoplanets. Some of these you might have heard about. You could look for a wobbling star. So let's say there is a planet orbiting a star. And when we think about a planet orbiting a star, you think of a star that's sitting there and a planet going around and around as it orbits the star. But really what's happening is that the gravity of the planet and the star are causing them to orbit each other. It's just that since the star is so much more massive than the planet, it's only kind of wobbling back and forth as the planet makes a really big orbit. Turns out we're really, really good at measuring how fast a bright object like a star is moving towards us or away from us. So even if we can't see the planet, we can sometimes see the star wobble. And then we can figure out, there must be a planet orbiting that star, making it wobble back and forth. And people have been using this method to discover hundreds of exoplanets around nearby stars. There's another method. Let's see, is this, doesn't start automatically. Let's try that one. There we go. So there's another method, which is a planet blocking the light of a star. So if a planet is orbiting a star in just the right angle so that its orbit takes the planet between our line of sight and the star, then when the planet goes in front of the star, it'll block some of the star's light and cause our measurement of the brightness of the star to dip a little bit. It'll make the star just a little bit dimmer for a little while, and the star will then go back to its regular brightness. If you look at millions of stars over time, you can then discover planets by looking for this telltale dimming of the planet, of the star. This is the method that I used with my project called CELT, using small robotic telescopes to monitor the brightness of millions of stars, and then we discovered our 26 planets by looking for those little dips that would happen over and over again each time the planet went around the star. So this is now at the end of the first part, and if anyone wants to ask any questions, we can pause here and take questions, or we can move on. Yes, questions back here. Go ahead.
It's very in the top.
Oh, he just wants to know, how do you get up to that?
Well, that's not my Shirley.
Yes.
What are you doing by Shirley?
How fast can a planet orbit a star?
So the question is, how fast can a planet orbit a star? So our planet Earth takes 1 year to go around our sun. Other planets, if they're closer to the star, they'll go around faster. So Mercury, which is our closest planet to the sun, goes around the sun every 88 days, I think is the orbital period of Mercury. Other planets that are really far away, like Uranus and Neptune, can take 20, 30, 40, 50 years to go around. So depending on how close you're orbiting the star, you can either go around very fast or very, very slow and long. And the planets that we discovered using our telescope go around really, really fast. These are planets that are really close to their stars. That's why they're called hot Jupiters. And they go around every few days.
Yes, I got it.
Yes.
I spend this all day.
What's that?
I spend this all day.
How many planets are there?
Oh, how many planets are there? So there are the 9. So there are the 8 planets in our solar system.
There's 9.
Clearly, I grew up before 2006. There are the 8 planets in our solar system, and we have discovered over 5,000 planets orbiting other stars in our galaxy. And later in this section, I will show you kind of a map of where they are. Yes.
So are these, like, the gas giants, I guess they have a very small core, and then all this, how does the gas stay?
So the gas giants, like Jupiter, they are made of gas, but they're very, very massive. Jupiter is, 300 times the mass of Earth? So even though they're made out of stuff that is, we think of as very light, that gas, that hydrogen and helium, has mass, and the self-gravity of that keeps it held together, even if there weren't a core of, say, heavier material like rock and metal. Now, we do think that these gas giants probably do have cores of rock and metal around which you have an envelope of hydrogen and helium, but we're actually not sure about that. There's a NASA mission right now visiting Jupiter called Juno, which is trying to answer the question of what does the inside of Jupiter really, what is it really like? And we're not really sure. All right, I got time for one more question.
How far can the telescope see?
We can see, with telescopes on Earth, millions of light years away. The planets that we're seeing are all planets that are basically close to the Earth in our own Milky Way galaxy. So they're usually tens or hundreds of light years away, and light year is a distance that we can measure things in space. But people who study distant galaxies can look at things that are billions of light years away. And they can see them because those things that they're looking at are very bright. So they're looking at galaxies or things called quasars. So, all right, quick question.
How many stars are there?
There are roughly about 200 billion stars in our own Milky Way galaxy, and we know of at least several hundred billion galaxies in the visible universe that we can see. So if you multiply 100 billion times 100 billion, that's at least how many stars there are. There's probably a lot more than that. All right, I'm gonna move on to the next section. Okay, so I told you about some of the ways that we discover planets. So back in 2009, NASA launched the Kepler Space Telescope. This was a telescope that orbited the sun, kind of trailing behind the Earth, and it stared continuously at one place in the sky. It's an area, the constellations of Cygnus and Lyra. And the idea was to look continuously at about 200,000 stars with a space telescope that was able to measure the brightness of those stars extremely precisely, and then to discover planets around them using the transit method, the method of waiting for the planets to dim because looking for the stars to dim because the planets were going in front of them. And it was wildly successful. I'll show a video here that shows this is a schematic putting together all of the planets discovered by the Kepler mission up to like the first few years. What you're seeing here is to scale. This is our solar system. So this is Mercury, Venus, Earth, and Mars. This is the size of the orbits. And you'll see that most of the other solar systems that we've discovered have planets that are orbiting way closer to their stars than our planets in our solar system orbit close to our sun. And that's mostly because this method of discovering planets by looking for these dips is really, really efficient. It's a lot easier to find planets that are really, really close to their stars, which is why most of them are really close. And you can see their color, the sizes of them show you how big the planets are. So you've got big gas giants like this, and then small rocky planets like that. And their colors tell you how hot they are, because their temperature is going to be connected to how far they are from their star, but also how hot the star itself is. Not all stars are the same temperature as our sun. So this is just a really cool, if you just go online and you Google the words Kepler orrery, I know orrery is kind of a funny word, you'll find this video, it's on YouTube, and it's awesome. You can just stare at this for a long time. So, after discovering thousands of exoplanets, what have we learned? Well, there's a few really key things that we've learned. One of them is that planets are common. We now know that there are more planets in our galaxy orbiting stars than there are stars. On average, there are more, every star has multiple planets. This is a huge result, because until we started making these discoveries, we weren't sure that planets were common. Maybe it was the case that our solar system was special in having planets and that most stars didn't have planets. That was a possibility that people considered. Now we know that's not true. Now we know that most stars have planets. We also know that small planets, like the size of the Earth and Mars and Mercury, are very, very common. In fact, they're a lot more common than big gas giant planets like Jupiter and Saturn. And finally, planets exist around all kinds of stars. And they can be in configurations and orbits that look nothing like our own solar system. For instance, in our solar system, all the planets orbit in pretty nice, even circular orbits, where all the planets orbit in the same plane. We've found other solar systems where the planets orbit not in circular orbits, but huge, elongated, oval-shaped orbits, or that are orbiting in basically perpendicular to the plane of their solar system, depending on how you think of that. So we've learned that there's a huge variety of planets out there orbiting a huge variety of different kinds of stars, from big, hot blue stars down to small, cool, dim red stars called red dwarfs. After Kepler, we launched the TESS mission. TESS was launched in 2018. So while Kepler looked continuously at one place in the sky to discover thousands of planets in that particular location by just not looking away and missing any of those dimmings of the stars, TESS observed the entire sky, and it's still up there and it's still observing. It's also discovering planets using that transit method, looking for the dimmings of the stars. And it's been incredibly successful. I think the other videos turn off.
Oh, they come in and out.
Oh, okay.
They'll pop back on.
All right. So now is where I'm going to take a break, and I want to show you all something called Eyes on Exoplanets. This is a website that is run by the Jet Propulsion Laboratory. It's the big NASA center out in California. So let's see if I do this right. There we go. Okay. Back home. This is one of those things where you have to like do your mouse without seeing the screen in front of you. Okay, so this is what you'll get if you go to Eyes on Exoplanets. It's really easy to find. You just Google Eyes on Exoplanets. This is an interactive website that allows you to see all of the stars in the sky that we know have exoplanets. And you can zoom in closer to our sun and see the planets that are orbiting stars really close to us, or you can zoom far away and see the planets that are orbiting stars that are far away. You can move this around and you can see things like, let's see how to do it. There we go. So this big jutting arm over here, this is where the Kepler telescope was pointed. That's why there's so many exoplanets in that direction. And so you can play around with this and look just at stars that were where we found planets from a specific telescope or mission. And if you click on one of the stars, which was that? 24 bonus. Okay, let's see. That will show you that system. Oh, the planet. Oh, is this like a really hot Jupiter there?
Yeah, it looks like it.
Yeah, so the planet is really, really orbiting very, very close to the star. And let's see, let me try a different one. I'm gonna go back to home. Let's try.
Can you search for a particular planet?
You can,
Upper right?
in the search button. So let's do 16 Sig. Oh, Here we go. This is a really cool system because,
Zoom out.
maybe we gotta zoom out.
Zoom out, zoom in.
So, this is funny. I'm gonna have to tell JPL that something's a little bit messed up here. I don't know what's going on. Let's try a different, let's see, Kepler 16.
Hypothetical visions.
There we go. Whoop. I lost it.
Maybe
Sorry,
zoom
it's very
way
hard
up.
kind of like looking there and like using the keyboard here. But you can look at, so this is a circumbinary planet. This is a planet that is orbiting 2 stars at the same time. I don't know
You
why.
might have to zoom way out.
What's that?
Can you click on the system to
Oh.
see a bigger view of it?
Yeah, let's try that.
And then hone in onto the plane?
There we go. Oh, yeah.
Yay.
There we go. Thank you.
Much better.
I created the site.
So you've got Kepler 16a and 16b, which are the 2 stars, and then the lowercase b is the planet that is orbiting both of them together. There is so much more you can learn by experimenting with this webpage, but I want to tell everyone about it that no matter how old you are, you can just learn a whole lot about exoplanets and the stars that they orbit with this tool. So I just wanted to share with everyone, and I mean, I could just sit and just stare at this thing for hours. It's so cool. Okay, so let me switch back. Okay, so the next thing I'm going to talk about is the search for life, but I'll take another quick break here and see if anyone wants to ask any questions about anything that we've talked about. Yes?
Are all the planets round?
Are all the planets round? Yes, mostly. So basically everything in the universe, once it is more massive than a certain size, all of that mass, all that gravity, is going to pull it into a round shape. So that's why all the planets are round and all the stars are round. Now there's a very small variation to that, which is that anything that is spinning will bulge out a little bit. So Jupiter, for instance, is about 10% larger at its equator than at its poles, because it's bulging out because it's spinning very, very quickly. Yes?
Have you found black holes?
Have I found black holes? I haven't found black holes, but other astronomers have found lots and lots of black holes.
Like
They,
unicorn.
what's that?
Like unicorn. That one's very close. That's the smallest one.
So black holes come in different sizes. There are stellar mass black holes that are what happen after a really big massive star explodes and leaves behind a black hole. But there's also supermassive black holes that have the mass of millions of stars that are at the centers of galaxies.
How about primordial?
And then there's a big question about primordial black holes from the beginning of the universe, and we're not really sure about them. So, okay, let's see, yes?
So you said, I think, that we only knew about our solar system up until 1992.
So there's a very complicated question about when we first discovered the first exoplanet.
Okay.
I subscribe, and it depends who you talk to, I subscribe to the idea that the first confirmed exoplanets that we all agreed on were the discovery of the pulsar planets by our friends at Penn State down the road, Alex Wolchan, who discovered planets orbiting at something called a pulsar, which is a neutron star. But the first planet discovered orbiting what we would call a regular star or a main sequence star was in 1995, and that's what they won the Nobel Prize for a few years ago, were the people who discovered that planet called 51 Pegasi b back in 1995. Yes?
I have 2 questions.
Mm-hmm.
Are white holes real? And can you make a new galaxy?
Okay, so the first question was, are white holes real? White holes are kind of a theoretical idea that are kind of like an opposite of a black hole. I don't think they're real. No one has found any of them, and I don't think they're real. The second question was, can you make a new galaxy? So it depends on what you mean when you think about make, but we do see new galaxies forming when we use our big telescopes like the new James Webb Telescope, looking back very far into the past, and we can see sort of primordial galaxies colliding and forming new galaxies as we observe them. So we can form new galaxies by combining multiple galaxies coming together. Okay, yes?
How does a black hole get made?
How does a black hole get made? So the kind of black hole that we know how it's getting made is what's called a stellar mass black hole. So stars come in different sizes. And the biggest stars, and are also the hottest and the brightest stars, the reason they're shining is because they're basically burning all of the fuel inside of them very, very fast, and they're creating all of that light and heat. When they run out of their fuel, they collapse down on themselves, and then they explode, and the core of that star collapses into itself and becomes a black hole. That's how black holes are. Okay, yes?
How many planets can orbit a star?
How many planets can orbit a star? We're not sure. We have the 8 planets in our own solar system. We have found other solar systems that have up to at least 6. I think there's 7. I think that we know of 7 planet systems, but those are only the ones that we found. It's very possible you could have solar systems out there with 10 or 11 or 15 or 20 planets. We're not sure. That's why we have to do some more searching. Yes.
Can black holes do damage?
Can black holes do damage? I wouldn't worry about that. Yeah, that's
They
yeah.
do so much damage.
So okay. So now I want to talk about the search for life, because even though we as scientists are very excited about finding planets and finding new things about the universe, one of the reasons we're really, really focused on searching for other planets is because planets are where there's life. And people have wondered forever, is there life out there, not just on Earth, but other places? So let's talk about that. The first thing I'll say is that while I'm an exoplanet astronomer and I'm really focused on looking for life outside of our own solar system, there's a lot of people who work really hard on looking for life in our own solar system. Even though we know that there's life on Earth, of course, people have been asking the question, is there life on other planets or moons in our solar system? And so they look at places like Mars. We've been sending rovers and spaceships to Mars for generations now, and we're really excited to look for evidence of life on Mars, either life now maybe, but really we're thinking about life billions of years ago when Mars was warmer and wetter. But Mars is a hard place to find life or even to have life because it's very, very cold. The typical temperature is minus 80 degrees. Its atmosphere is incredibly thin and is entirely carbon dioxide. So there's no oxygen if you wanted to breathe. It does have a lot of water, but as far as we can tell, all of it or almost all of that water is frozen into ice. So it's basically a very difficult place for life to live currently, even though back billions of years ago, we know that it was warmer and wetter and maybe there was life then. So Mars is hard. Another place that we've become a lot more excited about looking for life just in the last 10 years or so is a moon of Saturn called Enceladus. This is the moon Enceladus. It's a relatively small moon. It's still big enough to be round, but it's a lot smaller than other moons you might have heard of, like Ganymede or Europa. Enceladus, the surface there that you see, that's pure ice, water ice. It's H2O. It's frozen because it's very, very cold, but it's got a surface of pure ice. What we've learned over the last couple decades is that Enceladus seems to have something going on under that icy surface. And in fact, we've got pictures of plumes of stuff shooting out from underneath. What we now think is that Enceladus, as well as other icy moons like Europa, probably have liquid water oceans underneath the icy surface. And if you've got liquid water, it's a good environment to potentially have life. So we think that what's going on is you've got this icy surface on top, and then you've got a core underneath of sort of rock and metal, and then you've got this ocean between the two of them that has basically, just like we have volcanoes jutting out from the ocean floor, we can have sort of volcanic plumes shooting water up and out, because we saw those pictures of those plumes on Enceladus from before. So there's a lot of people working very hard to look for life in our own solar system at places like Mars and Europa and Enceladus. But If we're thinking about looking at other solar systems, we're having a hard enough time even hoping to find life under the icy crust of oceans, under the icy crust of moons in our own solar system. We can't even hope to probe that, to explore that for moons around planets around other stars. But we are thinking about, what do you want to look for planets that are orbiting other stars that might be suitable for life? So what do we look for? Well, we look for a few things. One of them is a solid surface. You want to have a solid surface because if, let's say you have a pure water world, a complete ocean planet, if you don't have a solid surface, you don't have a surface for the chemicals that form the kinds of things that life needs, amino acids and fats and hydrocarbon chains. You don't have a surface for them to get together on and mix together. So that's why you want to have a planet with a solid surface. You also want an atmosphere, because as I'll say in a second, the key thing that we look for when we're looking for life elsewhere is liquid water. The reason we look for liquid water is because if you look at a person, you see like, oh, we got skin and hair, well, hopefully you have hair, but you know, bones and teeth and fingernails, but really a human being and most living things are made up mostly of water. We're made up of water because inside our cells, all of the things that make us living have chemical reactions going on inside those cells. Those are the things that give us the energy and that get energy from the food that we eat and that enable us to move and think and do things. Those are chemical reactions happening that drive everything that a living thing does. And those chemical reactions, from everything that we understand, require liquid water. Maybe there's a kind of life out there that doesn't need to have liquid water. It could potentially be out there, but we wouldn't have a clue of even how to look for it. So that's why what we're looking for is we're looking for a place that's got liquid water, because at least there we would have some hope of recognizing life if we found it. And that's why you need an atmosphere. Because if you have a planet that's the right temperature, but it doesn't have an atmosphere, you can't have liquid water. The water would freeze or boil away right away. You need an atmosphere, you need air around to provide the pressure that allows water to be liquid. And then you need the planet to be at the right distance from its star, so that the surface of the planet is the right temperature that the water can be liquid. If the planet is too close to the star, then it'll be too hot and all the water will be boiled away. And if you're too far from the star, it'll be too cold and all the water will be frozen. So all of this combined is what we are looking for of other planets, to look for liquid water. And so we're looking for a planet with a solid surface, and that means a rocky planet like the Earth or Mars. It means having an atmosphere like Earth does, and it means to be at the right distance from the star to be in the habitable zone, at the right distance, so that the temperature on the planet would allow there to be liquid water. And that depends. It's the habitable zone, the sort of circle around the planet, around the star, where a planet can orbit and be at the right temperature, depends on how hot the star is. The hotter the star is, the further out the habitable zone is. So these are all the things that we need to play with as we look at these different stars and look for planets. So what do we do if we actually find a planet and want to look for life? Well, right now, the best way we can do that is if you've got a transiting planet, meaning one of those planets that goes in front of the star and blocks the light. Imagine looking at it from the side. So we're looking at it from the side here, and we're seeing the star shining. A lot of the light just passes by the planet, and this is a telescope. So imagine us looking through a telescope here, and we're looking at the light from the star. Most of the light just passes by the planet. A little bit of the light is blocked by the planet, but a tiny little fraction of the light from the star goes through the atmosphere of the planet. And something interesting happens when light goes through air or goes through a gas. It gets imprinted with certain patterns that have to do with what that gas is made out of. So if you were to take the light that is just shining through this room, and you were to break that light into all the different colors and different wavelengths of light, you would see the patterns and imprints of the nitrogen and oxygen and carbon dioxide in this air all around us. Well, if we can break apart the light that goes through the atmosphere of the planet, and then that triangle there represents a prism, meaning breaking it apart into the component colors, then you can look for the patterns that can tell you what that atmosphere is made out of. And if you can tell what the atmosphere is made out of, you can start learning about what are the conditions on that planet. And maybe even see patterns in the atmosphere that could be caused by life, by living things. So this is something that we've been doing with different telescopes, some telescopes on the ground, also telescopes in space. I think this was using, actually this was a combination of data from the Hubble Space Telescope and also the Spitzer Space Telescope. But now we've got a beautiful new telescope called the James Webb Space Telescope. It was launched on Christmas morning in 2021. And it is a gorgeous, enormous telescope that is floating out past the moon in a very nice, cool place where it can look at lots of things in the universe. It has discovered already tons of things about galaxies and black holes, but you can also use it to do those kinds of investigations by looking for the composition of the atmosphere of exoplanets. So one of the first results from it was from a planet called WASP 96b, that was the name of the planet, and it found this pattern that told us about water in the atmosphere of that planet. Water vapor, just like water vapor in our planet that condenses into clouds. Now this is a gas giant planet, so we don't think that there's life there, but it does tell us there's water there. And if we can do this not for a gas giant planet, but for a smaller rocky planet, that's how we're going to start looking for life. So how are we going to do that? Remember when I told you that earlier when we were looking at that image of planets orbiting a star and that we needed to do 1,000,000 times better than that image in order to find a small rocky planet like the Earth? That's what we want to do. So the project that I'm working on right now at NASA is called the Habitable Worlds Observatory. It is a sketch of a concept of a mission. We're very far from actually starting to build it. But the idea is we want to build a telescope like this that'll be operating kind of in the same way that the James Webb Space Telescope is operating, but it will have the ability, it'll be so stable and so precise, it'll be able to block out the light of a nearby star and see an Earth-sized planet orbiting that star. That will require us to block. Oh, sorry, I was going to stop this before. This is showing that one of the things that we want to do with this telescope is to make it robotically serviceable. That is, we want it to be in place and to be configured so that we can send a robotic spacecraft out there and resupply it and fix instruments if it breaks. It is if this telescope, if we do succeed in building this telescope, it'll take about 1.5 decades. We're looking at the early 2040s for this telescope to launch. But the idea is that this telescope will have the ability to block the light from the star and see a planet that is 10 billion times fainter than the star right next to it. And this is a theoretical image of what that would look like. This over here, the center, is where the light from the star was blocked. This is if we were looking at our own solar system using a telescope like that. Jupiter would be really, really bright because it's very, very big. Saturn would be pretty bright, especially because it's got its rings that reflect a lot of light. Venus is over here, and then Earth would be over here. We would see a tiny little pixel of an Earth-sized planet. We don't need to see all the details of the surface, though, because we would take the light that we get from that one little dot and break it apart into all its colors and look for the composition of the atmosphere or other chemical signatures that were reflected off that planet that would tell us about what it was made of. And we could look for things like gases in the atmosphere that could potentially be caused by living things. This is the dream. And what we would like to do is this blue line here. So this is a schematic of what our atmosphere looks like when you break out the light into all its different colors. The blue line is telling us how much light is coming through at different wavelengths. And these different shapes and wiggles tell us about things like oxygen and ozone, or water vapor, or the fact that there is vegetation on the surface of the planet, or methane that is produced by different kinds of living things and non-living things. So this is what we want to get out of that little pale blue dot that we would see. So that's what we're looking for. And this is our dream, is to build a telescope that can look for this. And we could be the first generation of human beings on Earth to ever really be able to look for life on a planet orbiting another star. And this kind of work, this kind of project of building these telescopes and designing these cameras and doing all this, these are what scientists like me, like our colleagues here at George Mason, have been working on our whole lives, because we get excited about this. But the only way any of this works is if we as an entire country decide this is something that is worthwhile and good to do. Because this is not something that makes us money. It is not something that helps us, cure cancer or build, better airplanes or cars or phones or anything. This is something that we do because we believe that it is worthwhile and valuable to learn more about the universe. And all of these things that I've been telling you about, the people who are paying for it are all of you. This is taxpayer-funded work by organizations like NASA, who rely on all of you to support this work. So I want to say at the very end to thank all of you who made this happen. And I hope this has explained and given you a good reason for thinking about this as something that is worth us to keep doing. So thank you very much.
So I'm hearing from the little birds on the roof that the clouds may be coming in, so we're going to limit to only 1-2 questions.
And I'll stick around afterwards if people want to keep talking after some people go on. Yes.
I was wondering what the next step is if you ever do find existing life on a planet or satellite. Because right now we stand on the stage finding it, or what's going to happen if you do find it?
The next step, if we find life, the first thing to do is that Habitable Worlds Observatory, we want to look at enough stars and enough planets that the results of that survey will tell us if life is common or rare. That's the first thing we're going to learn. But the second thing is, once we do that, then we build the next generation of telescopes and we start working on comparative astrobiology, looking at all the different kinds of life on all the different kinds of planets and start learning more about what that life is. That's the next step.
This is obviously extremely hypothetical and kind of absurd questions, but is there some kind of plan of action, what if we find intelligent life or intelligent life finds us?
So there's two. Okay, so there's looking for life, but then there's also looking for intelligent life.
Right.
So life could be just bacteria, microbes. But then there's intelligent life of anything that can build technology. There is actually a ton of work that has been going into the question of if we were to discover either just signs of life in general or signs of intelligent life, what we would do and how we would communicate that. In fact, I'm going to a workshop in a couple weeks that's all about figuring out the protocols, the rules for how we inform the world that we've discovered life. And we're going to start working on this now in hopes that we'll be ready years from now when that happens.
Right, I'm sure we would need linguists.
There's so many things we have to think. And the biggest problem is, in science, the first thing you discover is usually not going to be a slam dunk. The first thing you discover is going to be really tentative and uncertain. So do you start telling people, maybe we've discovered it? These are things that we are working out now between scientists and policymakers and everyone to try to understand that.
Yeah. Quick question. With all the spectroscopy they're doing on the different telescopes, what kind of spectrometers are they actually using in order to get them?
You mean what are the mechanisms, like prisms or prisms or gradients?
I mean, there's a bunch of different methods of spectroscopy.
There's many. There's tons.
And so I was just curious, what are they actually? I'm sure that all telescopes aren't using the same methodology.
No, so what we're working on are primarily spectroscopy in the visible, near infrared, and ultraviolet. So we're not talking about far infrared spectroscopy, and we're not talking about X-ray spectroscopy or anything like that. So we're talking about just within those regimes for a bunch of technical reasons. And as far as what sorts of spectrograph, I mean, I'm not really sure. Those are things that people who work on spectroscopy work on really hard. I usually work on the results of what they find from that.
Fair enough. Okay, cool.
Yes?
What are black holes made of?
They're made of whatever falls into them. They're made up of planets or stars or galaxies or tables or whatever falls into a black hole becomes part of a black hole. Yep. You're welcome. Yes?
Yeah. Are we limiting ourselves to life as we know it, or is there...
For now we are, only because we barely even know how to look for life as we know it. we're still struggling desperately to figure out the difference between a false positive and a true signal of a sign of life as we know it. We could go out and look for life in places like the valleys of Antarctica or the Death Valley or really inhospitable places and still be confused about whether we're finding living things in different configurations. So far, wherever we look on Earth, there's life there, all kinds of crazy extremophiles, which are things that can live in really extreme conditions. But right, so the challenge is we're still only kind of at the early stages of learning how to recognize life as we know it. And if you start kind of like speculating about life, like silicon-based life or life in a gaseous environment or things like that, we wouldn't even know where to begin. So that's the question we always say is like the reason we're looking for liquid water and we're looking in the habitable zone is not because we don't think that life can live anywhere else. We just wouldn't know it if we were to see it. So that's why we start. It's kind of like the old adage of you look for if you lose your keys you look under the lamppost, because if you lost them elsewhere you wouldn't find them in the first place. So you look where you could potentially learn something. Yeah.
Did this say like Venus may have or something?
This has been so a few years ago. Jesus, it is a few years now.
Yeah.
So some astronomers who looked at signs of the composition of the clouds of Venus claimed that they have detected a chemical called phosphine in those clouds. On Earth, phosphine, as far as we know, is only caused by biological processes. The clouds of Venus, however, are a very different environment. First of all, they're not water like the clouds on Earth. Those clouds on Venus, they're made of pure concentrated hydrochloric acid.
Damn.
I've been
blown by that.
Yeah, it is a crazy environment. So now the weird thing is, and this is just kind of a neat thing about Venus, at the height of the clouds of Venus, it turns out that even though the surface of Venus is incredibly hot, it's like 800 degrees Fahrenheit, I think. Yeah. It's at the height of the clouds. It turns out that if you ignore the fact that the air is all pure carbon dioxide and the clouds are hydrochloric acid, it's actually the same temperature and pressure as the surface of the Earth at the height of the clouds. So there's been speculation about whether life can live there. But first of all, the detection of phosphine is still very controversial about whether they have in fact detected it. Second, even if it is phosphine, it's not like we're not really sure if could life be the only thing causing it, or maybe there's another chemical process that doesn't involve life that could be causing it.
Right.
And so it's super preliminary, and there's a lot of people I know who are less than thrilled that has become a major area of discussion. But you want to explore everything that's possible, so maybe it is. I don't want to be telling scientists not to look for it. I'm doubtful about whether.
Yeah, I thought what I was thought was not the distant past or
No.
the future.
Well, there's a whole other set of questions about Venus. But for as far as life being there right now in those clouds and creating that phosphine, I'm doubtful, but I'm open for people to check it out and see if it's true.
Is Venus mostly volcanic?
Venus is a weird geology. As far as we know, Venus, unlike the Earth is like a rocky planet that has rocky plates that float on top of basically a magma mantle or crust underneath. Venus, as far as we know, doesn't seem to have plates. It has a much thinner crust that kind of flakes and breaks apart rather than moving in concentrated plates. We think it actually has a lot of volcanism, and I think like a few months ago, or maybe a year ago, someone believes that they have found evidence in some past observations of the surface of Venus, evidence of present-day volcanism. We can clearly see evidence of past volcanism on Venus, but now there's a lot of interest in discovering whether there's currently volcanism going on there, because that tells us a lot about the structure and geology of the planet.
Actually, go ahead.
Yeah, first, yeah.
All right, I have a few questions. Do we have time?
I got time, yeah. So yeah, you can go ahead and we'll come back and we'll trade back and forth.
One of them, the theoretical telescope you're working on.
Yes.
What would the theoretical range be of it? Like how
So because it's trying to directly observe planets, you can't look at stars too far away, because then the angle between the planet and the star becomes even smaller and smaller, even for like the technology of this future telescope. So in general, we think we're only going to be looking at stars that are within roughly a couple hundred light years of the Earth. We're not going to be looking at stars that are far across the galaxy or anything like that. We're looking at nearby ones. oxygens, because those are the most optimal for the method that we're using.
Okay.
Yeah.
My second question. How often are planets with oxygen-rich atmospheres detected?
With oxygen-rich atmospheres? So far, we have not detected. So we have to be careful about this. One of the signs of life, or that we think is a sign of life that we're looking for, is free oxygen. When we say free, we mean as oxygen in the same way that exists in our atmosphere of an O2 molecule, like two oxygen atoms combined into a molecule. As far as we know, there's not a lot of ways you can produce a lot of free molecular oxygen in an atmosphere without having life. Now, there's tons of oxygen elsewhere in our atmosphere combined into carbon dioxide, that's CO, or CO2 rather. So you can have oxygen without having free oxygen. We have never discovered any planet, exoplanet, that has free oxygen in its atmosphere, but we've got a lot of them, like I showed you before. The one that's got water vapor in the atmosphere, water vapor is made of H2O, so there's oxygen bound into that, but it's not free oxygen, so that's the thing. So we haven't found that yet.
That would be a big win.
It would be a huge discovery if we were to find that. It would be very, very exciting. We wouldn't claim it was life, but we'd claim it was the best lead towards life up to that point.
And the last one, when you brought up icy moons
Yeah.
in the solar system, the theoretical presence of oceans under the ice, are there any projects ongoing to study that?
Oh, yeah.
How would you, like, the pressure is immense. How do you get something?
So first of all, there's multiple projects going on right now. We're actually getting ready to launch, I think, is Europa Clipper going up next year? 2 years?
This year,
Is
actually.
this year?
It's
This year?
Yeah.
Oh wow, we're that close.
Yeah.
So we're sending a probe to Jupiter that will orbit Jupiter and swing really, really close to the moon Europa, which also is believed to have a subcrustal ocean. And it's just going to observe and test what it can observe from remotely to see is there further evidence of an ocean and how thick is the crust, what's the ocean made out of, and doing that in ways like of testing gravity, magnetic fields, and the composition of the surface. There have been plans for a Europa lander. That is a robot, like a robotic craft that would go to Europa, land on the surface, and then what I've heard as kind of like one of the design concepts is you bring along a brick of radioactive plutonium or something like that. That generates a lot of heat. You just put it down on the surface, you have a very long cable, and it slowly melts its way down through the ice, and then gets all the way down and carries along a probe, like a little probe that can actually sample water and maybe even swim around. The best idea I heard, the coolest idea was you actually have it trailing a little submarine that goes down and then swims around under the ice. I have no idea how realistic any of that is, but it is a conceptual plan that people have raised as a possible way of directly probing that. But you wouldn't even have to do that if you could just simply land on the surface and then just directly sample the frozen ice, which presumably has some of the contents of the erupted geysers from underneath. That would already tell you a huge amount. So again, we do step by step. Okay.
Yeah, I had a question similar to that, I guess. Just trying to figure out, like, why would one planet or one moon develop, be all ice, like in that scenario, versus another one?
So I can tell you sort of kind of like a just so story. So if you had, say, a cloud of rock and metal dust along with icy material around a gas giant planet like Jupiter, and then that material then formed into moons, then those moons that happen to form further away from Jupiter will be more likely to have ice on them, while the moons that formed a lot closer, where the planet was a lot harder, that ice will be boiled away, and so you wouldn't have as much ice, you'd have more rock. So you have a gradation, and it's kind of like in our own solar system, the planets closest to the sun don't have that much water and ice. Even as much water as we have on Earth, it's nothing compared to the amount of ice and water around the outer planets. So where the planets or moons form around like the local heat source affects how much water or ice they have. But then you have questions about what's called differentiation. That conglomeration of rock and metal and ice and gas, or whatever it is, that then settles and heats up and then sort of differentiates, and the heavier stuff sinks to the bottom, the lighter stuff floats upwards, and then you have the icy material up top and the rocky metal material at the bottom. That's why you have kind of the rocky cores. But why you have it like, why Enceladus out there, or Mimas out there, or Dione, or Titan. I mean, there are a lot of questions that we're just not sure why it happened in a particular way, and we're not sure how much of that is like what we call a systematic thing, like, oh, it always happens in this way because of the basic physics, or just a contingent way, which is, well, just how it happened in that particular circumstance, but it could have happened differently elsewhere if the conditions had been different from the beginning. So that's something that planetary scientists work really hard on, and that's what we want. If we find a lot more of these exoplanetary systems, then we can do a lot more comparative exoplanetology, and then ask these questions: which of the properties of a solar system are because of that? That's just the physics of how solar systems form. Versus, oh, some of them just happen to form like with a hot Jupiter, and others just happen to form with a lot of rocky planets. So that's something we're looking forward to.
So that moon you referred to?
Yeah.
So when we say water, is that considered H2O?
Yeah. So when I say
okay,
so yeah, this
so
is
my question was really like, why is that H2O and another planet would be more liquid?
Yeah. Our language is a little bit fuzzy on that. When we say ice or ices, we often mean the broad category of water, carbon dioxide, methane, ammonia. But when we say water, we literally mean H2O.
Wow.
So that's and I realize that could be confusing.
Yeah, no, but it's interesting why that planet, that moon has H2O.
Just